Hey, what's up, everybody? Mr. Tannen here. Just thought I'd try to go through a quick proof of the product rule um, because it is a tricky rule, but I think sometimes these rules can be dropped on us without us necessarily seeing where they come from. And most all of these rules can actually just be proven with the definition of the derivative using the limit definition, I should say. So you'll see here the constant rule. We talked about this a bit. In my mind, it makes a lot of sense. If f of x is a constant function, so c would be a number, its derivative is zero. Well, thinking about the tangent, slope of the tangent, well, it's horizontal, so the slope is already zero. Constant multiple rule. So if you have a constant being multiplied by a function, well, that's the same as just taking the derivative of the function and multiplying, which we've done a bit in the power rule. We're just multiplying by the coefficient. And again, the power rule, which Jose had found for us, which was quite cool, which not only applies to quadratics like he initially noticed, but all polynomials, um, which then makes the sum and difference rule quite helpful. That if we have multiple, terms or functions like we often do in polynomial form, we just take the derivative of each part, which is why the power rule works quite nicely for those polynomials. But then they start getting a little more complicated, like a lot of these rules function in ways that are actually nice and simple. But the product rule, you'll notice, if we have a function that is actually a product of two functions, let's say, um, if f of x were something even like a trigonometric function, like sine of x times x, or x times sine of x, you can't just take the derivative. It's not like this where we just take the derivative of each part of the product. It actually ends up being the derivative of the first part of the product times the second original function plus the first original function times the derivative of the second part of the product. So often I like to memorize it by thinking left d right plus right d left. They had it written opposite, but addition doesn't matter. So the left function times the derivative of the right plus the right times the derivative of the left. I like to think of it like that. Left d right, left d right. Oh my gosh, this is so lagalicious here. Left d right plus right d left. And it could be opposite. And d, remember, is taking the derivative. I just wrote dee because that's how I say it. Or you could say, of course, left or right d left plus left d right. The order doesn't matter. But I want to go through a quick proof. So you're not going to necessarily need to go through this whole proof once you see the rule, but this proof can be a little tricky when you first see it. So let's try to be a little careful here. So if I have two functions being multiplied and I'm taking the derivative, well, I could use the limit definition here. So same thing we've been working on, but instead now I've got sort of this product. And really we're going to have to do some real, oops, that should be a G, I wrote H. We're going to have to really do some, gosh, this keypad is not wanting to be very smooth for me today, but hopefully it perseveres. So basically it's just the same thing, except now I've got my multiple function, and that is all being divided by h. So on the surface this appears to not really do anything for us. So we're going to need to manipulate things a little to get this proof going. So what we'll do is subtract out and add in an f of x plus h times g of x to the numerator. And then note that we're really just adding in a zero, since here these two terms would cancel. So let me show you what I mean by that. So we've got the same thing here. So I'm going to add and subtract the same thing here. I may need to zoom out a bit to give myself some more space. So I've still got this here. But I'm going to subtract this f of x plus h times g of x, and then I'm going to add the same thing because that's not changing then the value here. Some of you who love proofs are going to love this because it's one of those things where you really have to manipulate this in a particular way to get to where we want to go. That whole thing is O over H, not a very straight line, but so notice that we added two terms into the middle of the numerator here, these two, minus and plus. So as written, we can break up the limit into two pieces. From the left piece, we can factor an f of x plus h here, and we can factor a g of x from the right piece. So doing this would give us this. I'll do my next step in green. So I've got the limit, once again, let me be consistent. I haven't taken any limits, so I've got to keep bringing that down. So I've got the f of x plus h, which I can factor out here, and that is being now multiplied by, well, I've got my g of x plus h minus g of x. Some of you may start to already see why I may choose to do that. And then I've got my plus the limit as h approaches 0 of g of x times, once I factor that out, f of x plus h minus f of x all over h. And then, well, really, rather than writing those in the numerator, I could instead write those, just as a coefficient of the entire rational expression there. So f of x plus h, and then I have that multiplied by this whole thing. And the reason I'm doing this step is because now you may notice, well, g of x plus h minus g of x over h, oh, interesting. That may look familiar from our definition of the derivative. So f of x plus, oh my gosh, forgot to put my g of x in front. G of x here, bada bing. That would be f of x plus h minus f of x all over h. Okay, so now we're starting to get somewhere, because at this point we can use limit properties to write, well, we're then able to then just take the limit of each part of the product, because with a limit we are able to do that, right? So we could break this limit up just to say that, well, let me put this back over here, that the limit as h approaches 0 of f of x plus h, well, I could now make that its own limit and then have this limit here. Well, looky here. So this limit now, if it's not already clear, is actually just the derivative of g. Ah, and then once I do the same thing over here, again, I'm going to need to zoom out. This limit over here is, as you can see, is actually the limit definition of the derivative of f. So what I could simply do is then just say, well, also the limit as h approaches 0 of this right here, well, h is basically 0. We could then evaluate it. This limit just evaluates to give me f of x. This limit just is g of x. This is the derivative of g of x, and that's the derivative of f of x. So now we can see that the derivative of this product is indeed just f of x, now that we can evaluate the limits, because when h is 0, that's just going to be f of x. That limit will be f of x, I should say. This is the definition of the derivative of g of x, or g prime of x. And then I'm just going to have the opposite over here, which is, as I said, our what we call the product rule. Which As you can see here, this will be left d right plus right d left. I think that's the way I had it. Yeah, they had it the opposite way, but like we said, it doesn't matter. But I think that's why I like to say it. So it's the left times the derivative of the right, left d right, plus right function, the original function, times the derivative of the left. Left d right plus right d left. Product rule. We got it. Good to go. Much love, everybody. Like I said, you won't have to memorize this process, but I think it's interesting to see that all of these derivative rules, they can actually be shown how, or you can see how we can derive these formulas, derive these derivative rules from the original limit definition of a derivative. Look forward to seeing you all in class today. Have a great day.